Okay, so this is transformations of any function. Okay, so if we have any graph, we may know the equation of it, we may not know the equation of it, and we could be possibly asked to transform it. Okay, now remember there are different transformations that we can have. Going back to GCSE level, we had rotations, reflections, enlargements, and what was the other one we had? Translations. Nice. Now translations are the most common transformations that we're going to have here. So we're going to focus on those mostly, but we will look at a couple of the others as well. All right, so I've got different diagrams for each of the different transformations. Focusing on the first one, so we've got y equals fx. So as I say, I've just generally said fx. That graph could be anything. If I have something stuck on the end of it, what does that do to our graph? Moves it up. If I had a negative value for a, what would it do? Move it down. So it's moving the graph up or down. So it says here, moves the graph of y equals fx by a units in the y direction. So we know it's going to be moving up or down. So here I've got my basic function y equals fx. If I had y equals fx plus a, oh, that's not very good, is it? But you know the idea. So this value here would be a. Now what do I know about a here? Because it's actually gone down. What do I know about a? A is negative in this case. Understand that? Okay, so if I have a number stuck on the end of a function, I know that it's going to shift it up or down by however many a is. So I've made sure that I've gone down here so you know that it can be going down even though it says plus a. Okay, because a can be a negative value. Okay, this next one, f of x minus a. Now, it may be worth considering things that we've looked at just recently in the quadratic graphs. If I had y equals x minus 2 squared, do you remember what happened with that graph?
Pardon?
Do you remember what happened to the y equals x minus 2 all squared graph?
It's like this.
Not quite, no. That's when it was a number in front of it. So if you remember, if that was my basic x squared graph, x minus 2 graph was exactly the same graph. It had shifted 2 units to the right. Do you remember this? Not really? Is it coming back a little bit? So my original function was just x squared. I've now got x minus 2 all squared. So I had a horizontal shift. Okay, and that's always going to happen if my value is inside the bracket. So if I have a bracket and the function is applied to that bracket, so in this case the function is the squared part, then it's going to be a horizontal shift. So it moves fx, so that, remember, that's our original graph, by a units in the x direction. Now note here, this is minus a, but it moves it in by a units. So remember, it's always going to the opposite direction than we might imagine. So up above, when we had a plus a, we moved up, and a minus a, we moved down. For this one, if we've got a minus a inside the bracket, we're actually going to go to the right. And if we had plus a in the bracket, we would move to the left. So this was an example of something we should have been familiar with. Now looking at this one here, if we're having f of x minus a, so I'm going to move it, which direction did I say? To the right. Good. So my whole graph is shifting to the right. So that means that this would be y equals f of x minus a, whereas this measurement here is a units. Okay? So whilst we're saying they're shifting, do we recall how we used to describe translations when we were doing those at GCSE level? Scale factor was for enlargement. That was rotation. It was across and up and down. Yes. Do you remember what it was called? It was called a vector. I didn't hear that, sweetheart. I'm sorry. Okay. Oh my gosh. Very aggressive. So we could describe this movement here as the vector 0, A. Okay, so translation of vector 0, A, because this top number was the horizontal and this is the vertical. Okay, so we could get really fancy and describe it using a vector. So that would be 0, A. In a similar manner, what vector would we describe this movement? A0, nice. All right, okay, so next one is, what's different about what we've got here? A negative sign in the front. Now, hopefully you remember, again, the parabolas are the easiest ones to remember, because what do we say about the fact that if it's negative in front, it's negatively sad? So that means that this graph has been reflected in the x-axis. Okay, so our negative fx would be a reflection in the x-axis.
So we're not asking God?
Yes. I mean, it could be that they give you a graph that looks like this. And they say, that's your fx. What would your y equals negative fx look like? And so you would know that it would be a reflection in the x-axis. Oh gosh, here we go. So you would draw that. Okay? So, as I said, you don't actually need to know the equation of it. As long as you see a picture, you know what effect this negative here does, you can draw that new function. Okay? And that's the crux of these kinds of things, is that you don't necessarily need to know what the function is, but you need to know how it affects the graph itself. Next one, this time the negative sign is inside the bracket. Okay, so when it's inside the bracket, what happens is it's now a reflection in the y-axis. Okay, so if we had this function here, oh gosh, here we go, this is going to test me, isn't it? Oh, that's quite good, Miss Harrison, well done. So this is f of negative x. So this is a reflection in the y-axis. All right, so here we've got some examples. Okay, so given the graph of the function fx shown here. Oh, shush now. Got far too excited. Oh my goodness. Apologies. So number 5. So this is where there's a number in front of the function. So Jishna, what were you telling me earlier? What happens if there's a number in front?
It's stretched.
It's stretched. Good. Now if there's a number in front, it's stretched in the y direction. Okay, so that means it's going to get tall and skinny. Okay, so if A is greater than 1, it's going to get skinnier. If A is less than 1, so in other words a fraction, it's going to get wider. Okay, so, oh gosh, these are the not as pleasant ones to draw. So let's choose that amount. Okay, so that would be my y equals a f x. I mean, it's not ideal, but that would probably be perhaps y equals 2fx, about. Well, it's not ideal, but so it's kind of double the height it was before. You happy with that? But notice that the x-intercepts here haven't changed. Okay, so those values are still the same, because the only thing that we've had to change is the y scale. Okay, so if there's a number in front, the x values don't change, but the y values are multiplied by whatever that number is. Okay. And here we have a value inside the brackets. Okay, so what that does is it's going to be now stretched on the x-axis, but the factor is 1 over a. Now what that means is that if you've got a value, say for example, if you've got y equals f of 2x, then it's going to be stretched by a half. In other words, it's going to be half the measurement it was before. If you have y equals, or I should colour, y equals f of a half x, then it's going to be double the width that it was before. So let's see if we can draw both of those on here. So if we're doing the 2x first, we're going to be half the measurements we were before. So if this one was here, I'm now going to be about here. If this one was here, it's now going to be about here. And then we're going to go up, down. Oh, shush now. Oh, yeah, that's right. Oh, that's kind of okay. We happy with that? That wasn't great. So it may look a little bit similar to the translation, doesn't it? It kind of looks similar to that. But the fact that it's gone through this same point here tells us it's not a full-on translation, because if it had, the graph would look exactly the same as it did before, but we can tell that this one's skinnier on the x-axis. If we were to try and draw the blue one, that means that it would be stretched wider. So if this was our original point, it would be perhaps here. If this one was here, it would perhaps be here. So we would have that as our half x. Okay, so it's stretched wider.